Okay, this is video 24.2 where we're actually going to learn about Gauss's law. Now, you recall from the previous video we defined electric flux as the number of field lines that go through a surface. Gauss's law deals with electric flux. So first we're going to define what we mean by the phrase a Gaussian surface, because we'll be using that term a lot. Basically, a Gaussian surface is an imaginary closed surface. We're going to find a flux through it, but the fact that there's no actual physical object at the location of this surface is okay, because it's imaginary. And because it's imaginary, we can pick it to be any shape we want as long as it's closed. But we're going to find that certain shapes of Gaussian surfaces make it easy to calculate the electric field, and other shapes of Gaussian surfaces make it really hard to calculate the electric field. So let us now consider a Gaussian surface, which I'm going to draw as a blob, and there is no charge in it. The question is, what is the net flux through the surface? Now, if there's no charge in it, that means there's no electric field lines that will begin or end in the surface. And so any field line that goes into the surface has to then come out of the surface. And vice versa. So there are no field lines that begin or end inside the surface. And since the field lines that go into the surface count as negative flux, and the field lines that come out count as positive flux, the result is that if there is no charge, or no charge inside the surface, the net flux is going to be zero. Doesn't matter what the electric field is, if none of the charge that creates that field is inside the surface, the flux through that surface will be zero. Very, very important thing. There is obviously charge somewhere outside the surface, otherwise there wouldn't be an electric field, but if there's no charge inside it, flux is zero. Very important thing to remember. Now let's say we've got one positive charge inside this Gaussian surface. So here's the Gaussian surface. Let's say we put one positive charge in there. Let's say that 6 field lines come off of that positive charge. You've got a certain amount of flux, and so in some units, flux is going to be 6. If we've got 2 positive charges inside this Gaussian surface, each one produces 6 field lines. The field produced by them will look about like this. And notice that there are now 12 field lines coming out of this surface. And so the flux in those units will be 12. If, on the other hand, we have a negative charge inside it, that negative charge will have 6 field lines that end on it. And since that means 6 field lines are coming into the surface, the total flux through the surface will be negative 6. And one very interesting thing we can see from this is that the net flux through the surface is proportional to the charge. And so there's a couple interesting things here. We're concerned with the net flux, so the total number of lines coming out minus the total number of lines going in. And we're looking at enclosed charge. So any charges that are outside of the Gaussian surface don't affect the net flux through it. They may mean that there are additional field lines going in, but those field lines are going to have to come back out at some point. That is Gauss's law. Net flux is proportional to the enclosed charge. Mathematically, that says net flux equals the enclosed charge divided by this vacuum permittivity that we saw before. Remember, K, Coulomb's constant, is 1 over 4 pi times the vacuum permittivity. We'll see where that comes from on the next slide. And now, the flux is usually written as E dot dA, and there's a little circle on the integral that indicates it's around a closed surface. That is something that threw me off for about a week when I was in AP Physics C, and so I just want to bring that out right now. But that little circle just means that you're integrating over a closed surface. And then you've got the enclosed charge, and then epsilon 0 is a constant. Most of the time, E will be constant over the area of the surface, if you choose your surface correctly. And so the equation will look like that, which is much easier to deal with and doesn't look scary. This integral is not, well, it's a scary integral if you pick your Gaussian surface wrong. If you pick your Gaussian surface right, the integral becomes very easy. Okay, and now let's look at an example. Let's say we've found that the electric field in part of the Earth's atmosphere is directed vertically downward. At an altitude of 300 meters, the field has a magnitude of 60 newtons per coulomb. At 200 meters, so 100 meters lower, the magnitude is 100 newtons per coulomb. Find the charge contained in a 100 meter cube. So here's our cube. The bottom of the cube is at 200 meters, the top of the cube is at 300 meters, and it's 100 meters on the side. The electric field is directed downward. It looks like that. Now we're looking for the charge contained in the 100 meter cube. So we're going to use Gauss's law, and we're going to rearrange it a little bit so that the enclosed charge equals the permittivity times the net flux. Now we need to calculate the net flux. Well, first off, it's going to be the flux through the top, plus the flux through the bottom, plus the flux through each of the 4 sides. And we'll also see, okay, the flux through the top, because the field points inward there, it will be negative. So phi top is equal to negative EA. Because the field is perpendicular to that surface, and E is 60 newtons per coulomb, A is the area of the square, which is 100 meters squared, and that works out to be 6 times 10 to the 5th. Units of flux are Newton meters squared per coulomb. Now the flux through the bottom will be positive because it points outward, and that will be the field at that location, 100 newtons per coulomb, times the area of the bottom of the cube, and that works out to be 1,000,000 Newton meters squared per coulomb. If we look at the flux through the sides, we'll see that the field lines don't actually pass through the sides of the box at all. So the flux through the sides is equal to 0. And so the enclosed charge is equal to epsilon 0, which is 8.85 times 10 to the negative 12th coulombs squared per Newton meter squared, times the total flux. The total flux is 1,000,000 plus negative 600,000, and so the total flux is 4 times 10 to the 5th Newton meters squared per coulomb, and that works out to be, the enclosed charge is 3.54 times 10 to the minus 6 coulombs, or 3.5 microcoulombs inside that box. Not too bad. Now, a couple more things to look at. Let's look at Coulomb's law again. So we've got a single charge in a spherical Gaussian surface. So I'll say that charge is plus Q, and I'm going to draw the Gaussian surface, which is imaginary, by the way. I can draw it any shape I want. I'm going to make it a sphere. The reason I'm going to make it a sphere is that I know that the field due to this has spherical symmetry, meaning it's the same at every point on the sphere. Because all the points on the sphere have the same radius. And so if I draw the electric field lines for this, because of that, this integral E dot dA, which is the enclosed charge over epsilon 0, that integral just becomes E times dA, because E is a constant. And that integral dA is just the total area of the sphere. Now the surface area of a sphere is 4 pi r squared, and so that means I need to define the radius of the Gaussian sphere to be r, equals Q enclosed over epsilon 0. And then if I rearrange this to get E, I get 1 over 4 pi epsilon 0. The enclosed charge is that charge Q divided by r squared, which is Coulomb's law. So you can derive Coulomb's law from Gauss's law. Very useful. Well, not actually very useful, but it's reassuring that the two give us equivalent answers. And the last thing we're going to look at in this video is a conductor that has excess charge on it. So I'll draw a conductor. Remember, when we put excess charge on the conductor, it all goes to the surface of the conductor. So that means if I draw a Gaussian surface anywhere inside the conductor, the enclosed charge will be 0. A result of that is that the electric field equals 0 everywhere inside a conductor. That is a general result that you should memorize and be able to explain why. You draw a Gaussian surface. As long as that Gaussian surface is entirely inside the conductor, the enclosed charge is 0. And because that is true of any Gaussian surface in the conductor, that means the electric field inside the conductor is 0. Proving that rigorously mathematically is tremendously difficult, but it makes intuitive sense. And so now, for tomorrow, look at question 4, problem 5. I will be checking them.